Okay, ladies and gentlemen, let's talk a little bit more about probability. And in this case, we're going to get a little bit more complex. Now, let's just do a quick review. Classical probability says that your probability is your number of possible outcomes over the total possible. Another way to say that is successes over trials. Now, successes are the things that you're looking for. Trials, of course, are all the results that you get. So let's make a new chart for this. We have purple, green, orange, red, yellow. And I have 5, if I look in here, I have actually 3 purple. As far as green, I have 5 green, I have 1 orange, I have 5 red, and I have 1 yellow. Now, I didn't necessarily pick those. That's just what happened when I poured them out of the box. But we know that to get a classical probability, we need to know how many we have. So again, I got 3, 5, 8, 9, 14, 15. So we know it's 15. We know it is 3 out of 15. 5 out of 15, 1 out of 15, 5 out of 15, and 1 out of 15, which gives us 15 out of 15, because remember, probability has to equal a total of 1. Now, we also know that 3 out of 15 is 0.2. We know that's going to be 0.3 repeating. We know this one, gosh, I don't know what that one is. We're going to have to find out here in a minute. And again, it's not bad if I got to use my calculator. I just have to use it in appropriate places. So here we go. Let's grab the calculator. And it says 1 divided by 15 is... Now, in this particular case, I'm not sure. There we go. 0.06666666666666. So I'm going to go 0.07. 0.07. One thing that you might find is because the 3 is repeating forever and ever and ever, it may cause us a little bit of issue, because if I tried adding these up, would they all add up to 100%? Not exactly, because fractions are going to be exact, decimals are approximations. Now, we also talked a little bit last time that the notation, if I wanted to pull a green, let's not take my bucket, even though I could do that with experimental probability. We have the math. The chances of getting the green would be 5 out of 15. Okay, that would be the experimental probability. So probability of getting green, 5 out of 15. Probability of getting purple. Probability of purple, 3 out of 15. Okay, so we'd have a 0.3 repeating and a 0.2. Now, that's using just the math to find the probabilities, that classical or theoretical probability. But let's talk a little bit about with replacement and without replacement. So if I talk about with replacement and without replacement, it's going to make a difference, because here's the thing. Replacement means I put it back. So I pull something out. Oh, hey, it's a red. If I put it back in, that's with replacement. I replace it. I put it back in the bucket. If, on the other hand, I take the red and I set it right down here, now I go to choose again. Is the probability of getting a red the same now as it was when I had the replacement? Let's make it even tougher. Is the probability of a green now the same if I chose my red and left it out? Is the probability of getting a green the second time the same as it was when I did it the first time? Well, here we go. The answer is, as long as you use with replacement, all the probabilities will be the same every time I do it. I get a green. I put it back, do it again. I get a purple. I put it back, I do it again. I get another purple, I do it again. I get a red. And all of these probabilities stay the same. But as soon as I start taking something out and eating it, it changes. because I just ate a red, which means without replacement, my new chart looks as follows. It's now purple is 3, green is still 5, orange is still 1, red is now something else, and yellow is 1. How many reds? 4. But see, that's not the only change that we made. If that were the only change, that may not be that big a deal. But now, if I add them up, there's only 14. So now it's not 3 out of 15 like it was before. It's now 3 purples out of 14, 5 greens out of 14, 1 out of 14, 4 out of 14, and 1 out of 14. So the question earlier was, does the chances of red change if I don't put it back? The answer is yes, it does change. Okay, because there's 1 less red. It's in my belly. All right, but even the greens changed because 5 out of 15 was 0.33333. 5 out of 14 is now 0.36. So now it's changed. And so every one of these numbers would change. So with replacement, without replacement makes a huge deal. It also means that we have to talk about another term, and that is independent versus dependent. Now, if you're a person who is independent, means you get to choose, you do whatever you want, you have freedom. Dependent means you have to depend on somebody else, like I have to wait on a ride from my friend or my mom or my dad or my brother or whatever. In the case of flipping a coin, that's one event. If I do it again, that is totally independent, because when I picked this coin up, I picked up both the head and the tail, and so both options are back in, and the probability of which one doesn't change at all. So I could flip this 1 time, 10 times, whatever it is, and it's always going to be independent, where one trial does not affect another. So one trial does not affect another. Well, then what is dependent? Well, dependent means when one trial can affect another. Not an English teacher. That's okay. In this case, the chances of the green are now dependent because I took the red out, and now every probability depends on that one that I got the last time, because had I got a green the first time, that would have made the probabilities based on green, but because I got a red the first time, it's all based on red. And so it makes a big difference. This really becomes important when we do or and and. Or and these are called composite or compound probabilities. Composite or compound probabilities. I need another marker. Because if I want, what's the probability of getting a red or an orange? Well, in my original list, I can simply take the probability of getting a red, 0.03, probability of getting an orange, and that's 0.07, and just add those two up. Now, if I'm just looking for a red or an orange in one pull, that's not so bad. But the problem is when I try to get the probability of a red and an orange, now it becomes very important that I have independent trials, because if on the first time I pulled a red, that's going to change the probability if I don't put it back. So with replacement, without replacement, independent, dependent, all matter, and or and make a difference. Now, for or, the big key is using a plus sign. For that red, probability of red, we had 5 out of 15, plus the orange, which was 1 out of 15, so our chances were a total of 6 out of 15. Now the nice thing is it becomes easy to get because or means I win if I get this, or I win if I get this. Let's go to and. And is not inclusive but exclusive. And exclusive means if I need an R and a red and an orange, I only win if I get this one and this one. I have to have them together rather than this one wins and, or this one wins. So in this case, the probability of red was 5 out of 15. Again, it still only works if I put it back in. So we're using with replacement, independent, and this time the key math term is multiply. So I'm going to multiply by orange. So here we go, multiply by orange. 6. So then in this case I have 5 out of 15, 1 out of 15. That's going to make 5 out of 225 because 5 times 1 is 5, 15 times 15, 225. Look how much harder it is to get an and, get both of them, than it is an or, one or the other. In this case, 6 out of 15, that's not bad. What kind of percent do I have of getting a 6 out of 15? 6 divided by 15 is 40% chance. That's pretty good. 5 divided by 225. In this case, 0.02, which is 2%. So which one would you rather bet on? What's the probability of winning? I want or, not and. So that's and, or, independent, dependent. Composite, compound means I put two things together, and it has to be done with replacement or it doesn't stay randomized.